moving on to question number 16. A rod AB of mass m and length L is lying on a horizontal frictionless surface. A particle of mass m traveling along the surface hits the end A of the rod with a velocity v0 in a direction perpendicular to AB. The collision is elastic. After the collision, the particle comes to rest. A. Find the ratio small m by capital M. B. A point P on the rod is at rest immediately after collision. Find the distance AP. C. Find the linear speed of the point P at a time pi L by 3 V0 after the collision. So in this question, we are not given the diagram. We need to visualize it on our own, right? So let's start with the solution.
So now here, since we know that everything is ideal, they have mentioned elastic collision, we can first start with the diagram, and let us say, if suppose this is the so now in this question, suppose we start with the diagram, we can see that if this is the rod and a point P is on rest, so we don't need that right now. We can see, let's assume this O as the center of mass, and let the other small m be coming from here, let the capital M be here. This collides, and in the final situation, this m is at rest over here, and this m is moving ahead with some rotation also involved over here, and some velocity, say v. Right? So this is the situation that is happening over here. Now, since there is elastic collision, we can work with conservation of energy, conservation of angular momentum, and everything, since there are no losses involved. Right? So let's start with conserving only the linear momentum of the system. The initial velocity, if it is given as v0, the initial linear momentum will be m v0, and the final momentum will be capital M into v as the small m comes to rest. So this will give us that v is equal to m v0 by m. This is what we gained out of the linear momentum conservation. Next, moving ahead to angular momentum conservation, we see the initial angular momentum about the center of mass was m v0 into L by 2. This should be equal to the final angular momentum about the center of mass just after the collision, which will be equal to I into omega. Here I will be equal to ml square by 12, as we know, for a rod, for an axis passing through its center of mass. Therefore, mv0 L by 2 is equal to half ml square, 1 by 12 ml square into omega, which will give me omega as 6 mv0 by m into L. Right? Now I have an expression for V, I have an expression for omega. I can easily move ahead to the conservation of energy now. Since I have exhausted my angular momentum and all those conservation and got nothing out of them, I move on to the energy conservation and use these relations which I have derived right now in terms of known quantities. So the energy conservation will give me the initial energy as half mv0 square should be equal to half into capital M into V square, which is the translational kinetic energy, final translational kinetic energy, plus half into ml square by 12 into omega square, which will be 36 m square v0 square by m square into L square. This is the rotational kinetic energy of the rod, this is the translational kinetic energy of the rod, and this is the initial kinetic energy of the incoming mass. Right? Now, solving all of this equation, we will reach to a conclusion wherein we will get, after putting in the values of the initial values which we will find out, like omega as I have already put in, and V if we put in as mv0 by m, which we had derived earlier over here. If we put these two equations into this energy conservation equation, this one over here, this one over here, this will give me the ratio of m by m as 4. Okay, this is a very simple just substitution. Everything comes in terms of m and m, and you get capital M by small m equal to 4. The question asks us for the ratio of small m by capital M, which will obviously be 1 by 4. This gives us the answer to the first part of the question.
Right.
Now moving on to the next part of the question, which says a point P on the rod is at rest immediately after the collision. Find the distance AP. Now for this part, we'll have to write down the velocities of every part of the rod just after the collision, right? So for that thing, what we can do is we'll draw this diagram again. Let us see if this is our rod. Just after the collision, the rod will still remain vertical since it's just the next moment. This will now have the velocity of V, the center of mass. The points above the center of mass will be moving on in this direction with a velocity of R omega minus V with respect to ground. This R omega comes because with respect to this center of mass, they are moving in this direction with R omega minus V because of the motion of center of mass. This R omega is with respect to center of mass. So the velocity of this point with respect to ground will be this velocity minus the velocity of center of mass. Right? And let us say if this point is there over here, it will be moving in this direction with R omega plus V. Right? So now we see if, let us say this point will always have a positive velocity at the right at the next instant of the collision. So this obviously can't be the point P, as this can never be 0 just after the collision. So the point P has to lie above the center of mass over here, right? So this point P will be a point at which the value of R, which is this distance, will be such that R omega minus V is equal to 0. So we get R omega minus V equal to 0, which will give us R as V by omega, right? Now we know that omega is equal to 3 V0 by 2L by this equation over here. We know that m by m is 4, so that will give me omega equal to 3 V0 by 2L, and so I'll get V equal to V0 by 4 by putting this relation into this equation, right? I know m by m over here, so I know that V is equal to V0 by 4, and I know that V is equal to, so these are the two equations which I already have over here with me. I know that R is equal to V by omega. Now I'll divide V by omega to give me R, and R will come out to be V0 by 4 divided by 3 V0 by 2L, which will give me R as L by 6. Now moving on to the last part of the question, it says after time t equal to pi L by 3 V0, right? Now to analyze the situation at this time, first of all we need to know by how much angle has the rod rotated. Now we know that omega is equal to 3 V0 by 2L, right? So we'll basically do theta equal to omega into t, which will give us pi by 2. Now here we see that the rod has rotated by an angle of pi by 2. So the situation somewhat becomes like the rod has become this way. Over here it is rotating with omega. Point P has now come over here. Its velocity will be somewhere over here. Now velocity of P is what we need at this moment. So the velocity of P will be in two components. The first component will be this one, which will be in this direction given by R omega, and the other component will be in this direction, which will be the velocity of center of mass. Because we need the velocity of point P with respect to ground, we always add the velocity of center of mass to the velocity of point P with respect to the center of mass. Now assuming this direction to be the y direction and this direction to be the x direction, we get velocity of point P as minus r omega I cap, velocity of point P, plus velocity of center of mass, which will be v j cap, right? Now we know that v is equal to v0 by 4, and r omega will again be equal to V0 by 4 from our initial calculations. So this will give me the value of speed of point P as under root of V0 by 4 square plus V0 by 4 square, which will be equal to V0 by 4 into root 2, or we can write it as V0 by 2 root 2. This is the required value of the speed of P at time t equal to pi L by 3 V0.
Right. So with this we come to the end of the chapter rotational motion. In this chapter we saw some very important concepts related to rotation of bodies, like the moment of inertia, the conservation of angular momentum, the concept of angular momentum. We also saw the analogy between rotational and translational motion. So this question is extremely important from competitive exams point of view, and we should, as in, see, there are the basic rules, the basic
Right.
laws, like law of conservation of linear momentum, law of conservation of angular momentum, law
Right.
of conservation of energy,
Right.
mechanical energy.
Right.
All these need to be applied, but with them we need to be clear on the basics of mechanics.
Right. You
Right?
need to know where you can use which law.
Exactly.
You should remember that from all these problems. Those are the basic concepts which I've covered in all these problems which we did so far.
Right. So thank you very much.